On, I think I'm going to do a definition on, or I'm going to do a derivation for the moment generating function for a binomial distribution. And also what I'm going to do is part B, which is I'm going to use the MGF, and this is kind of the beauty of it all, is I'm going to use this MGF to find the mean and the variance of the binomial distribution, a random variable with binomial distribution. Okay, some relevant equations that I think we might be using in this proof are going to be, I don't know, let me just write a few down. I think I'm going to go with P of y is equal to n choose y, p to the y times 1 minus p to the n minus y. And yeah, I think that would be good. That would be my, this is the probability for a binomial distribution. And then also a relevant equation is the binomial theorem, which says that if you have the summation of from x equals 0 to n, then of n of x, y to the x, z, n minus x, then that's equal to y plus z to the n power. Let me just double check that equation. Yeah. The thing about it though is, let's see, I'm going to start changing some numbers around just because I want to try to remain consistent as far as not mixing up my y's and x's and all that kind of stuff. So let me just kind of take a look at what I'm going to try to do. Yeah, right. I'll write down the binomial distribution like this. If I have the summation from I equals 0 to n of I, then I'm going let's say, a to the n minus I, b to the I, then that's equal to a plus b to the nth power. I just wanted to make sure I didn't mix up these n's and y's and all of that kind of stuff, so I'm trying to keep them all separate. All right, so going into deriving for the MGF, the equation says that your moment generating function as a function of t is the expected value of this crazy thing, e to the t, let's say a y, e to the ty. And that's equal to the summation of y equals 0 to infinity, or in this case it's n, because our moment generating function, or because our probability only goes up to n, of e to the ty times the probability of y. So this is the way you start every single one of these problems, regardless of whether or not you're doing a binomial distribution or anything else. The thing about it is now we can plug in our binomial distribution that we looked up for that specific p of y. So just plugging that in, that goes y equals 0 to n of e to the ty, and then I'll have n y p to the y 1 minus p to the n minus y. Yeah, I think that's right. Okay, I'm going to clump these guys together because this is to the y power and to the y power. So let me just go y equals 0 to the n of p e to the t to the y. And then I still have my n choose y. I think of that as more as a coefficient, so I put it out in front. And then I'll have the 1 minus p to the n minus y. Cool. Let's see. Let's see. In this case, I'm going to compare this to the binomial theorem that I have here, and it looks to me like in this case your y is actually an I. So comparing, my I in this equation up here is equal to my y in this equation over here to the left. And my a is the 1 minus p, and the b, that would be the p to the e t. Is that correct? Yeah, that's right. So if I compare that, and I can basically just quote this part right here, I would simply write a plus b, so that would be 1 minus p plus p e to the t to the nth power. Yeah. Oh yeah, and comparing my n is equal to n. Those n's are the same. All right. So that's the equation. I think that the way I normally see it is this: p e to the t plus q, where q is equal to 1 minus p. Or I think that that might even be where what we need to prove. But essentially that's the same thing. It's p e to the t plus 1 minus p. I think this is technically the best answer. I like thinking of it like this. I think it's all the same in the end. All right, now what we're going to do is we're going to use the generating function to derive the expectation values. So the expectation values, the e of y, well, that's equal to m to the first derivative, and that's usually m of t, but this time we're evaluating it at 0. So if this is my m of t, then in order to find this guy, what I need is I just need to take the first derivative of this thing. So that would be, let's see, d dt of p e to the t plus 1 minus p to the n. Let's see, I'm going to pull down the n, so I've got n times p e to the t plus 1 minus p to the n minus 1, and then I'm going to take the derivative of the inside of that thing. That would be the, I think that's the chain rule, right? So then you go p e to the t. Cool. And then what I want to do is I want to evaluate this at t equals 0. So at t equals 0, this becomes n times p to the e0 plus 1 minus p n minus 1 p e to the 0. By the way, e to the 0 is equal to 1. Anything to the 0 is 1. So really I have n times p plus 1 minus p. Those guys are going to cancel out inside there. P, and then this would be n times 1 to the n minus 1 to the p, but anything 1 to the anything power is equal to 1 still, so I can get rid of that as well, and so this is equal to np. So my expectation value is equal to np. All right, and then finally, if I wanted to find var of y, also abbreviated v of y, then I simply find, well, I got to find e to the y squared, and then I got to subtract e to the y squared. I know it sounds the same when I do it, but I'm doing something a little bit different. The square's in a different spot. So if I want to find e to the y squared, that's just the double prime of the generating function evaluated at 0 as well. So what I have to do is I have to take the derivative of, well, that would be this one right here before I evaluated it at t equals 0. So that would be the derivative of this, p e to the t plus 1 minus p n minus 1 p e to the t. All right. So taking the derivative of this could be a little bit dicey, but it's not that bad. We got a product rule that we have to deal with here. So let me just do this carefully. I'm just going to write this all out. This is going to be equal to, let's see, And I'm going to take the derivative of the second one first, just because that seems like it's way easier. And then I'm going to put a plus sign, and I'm going to take the derivative of the first. So I've got n times this thing, n minus 1, and then that would be p e to the t. Taking the derivative of p e to the t is still just p e to the t, so that doesn't really change anything. Then I'm going to put a plus sign, and then I'm going to write out these two terms. So this would be np e to the t. I'm going to take the derivative of this thing right here, the first one. So that would be n minus 1 p e to the t plus 1 minus p to the n minus 2. Whoa. Sorry, pen slipped right there. N minus 2, and then it's PET. That would be the chain rule tells me to take the derivative of the inside as well. So that's a pretty complicated, crazy thing, but it's not so bad because all I have to do is evaluate it at t equals 0. And so plugging in t equals 0 into here, I'll go with n times p plus 1 minus p to the n minus 1 p plus np times n minus 1 times p plus 1 minus p to the n minus 2 times p. Alright. And then these guys what they do is they're just equal to 1. So I have np plus np squared. Uh-oh. Come on, computer. Np squared times n minus 1. Cool. And this is my e of y squared. Now if I want to find my variance, I have to take this thing and subtract off the square of this thing. So var of y is equal to what's above subtracted np, which is my expected value, squared. So let's see, np plus n squared p squared minus np squared minus n squared p squared. This cancels out with that, and I get np minus np squared. And then factoring out an np, I'll go with 1 minus p. And I think this aligns with what our book derived. Admittingly, this is not the easiest way to derive the expected value and the variance. However, this is a use for the generating function, and maybe using the generating function would be the easiest way to derive the expectation value for other complicated things. So this is kind of just really to show you an application of the moment generating function. However, it's probably would be way easier if you were talking about the binomial expansion to do the problem, a different way if you wanted me to find the expectation of variance. But I hope that helps.